Hi. Well, the presentation has been made, so I think we can dig into the subject right away. The first thing I want to mention, maybe I have this stuff that's going to be better, is that like memory is slow. It shouldn't be unused by now. Like many people involved with kind of performance work know that. It's not working. Okay, we're gonna use our hands. So it's about 300 cycles on modern machine to hit the memory. You can do a lot of stuff during 300 cycles. The bandwidth is still increasing, but the latency is like almost not increasing anymore, and not even remotely at the same rate as the CPU speed increase. So the gap gets wider and wider over time. So to work around that, CPU use caches. Shouldn't be a big news also for many of you, but it's always good to be reminded. So you have different level of caches in your CPU, and the smaller they are, the faster they can be. So there's different level, some very small and very fast, and some larger and slower. And typically, you have like the first level is a handful of cycle, and then tens of cycle, and more and more. And the caches are split by cache line. This is going to be important later. So the memory operation, when you program, you load bytes, you load like integer, you load this kind of stuff. But the cache itself works in chunk of 64 bytes. And this is gonna be important. But first, I wanna say a little story. So this is the story of a king. He wants to throw a party, and he has a giant cellar with 1,000 bottles. And sadly, there is an evil man, and he poisoned one of the bottles with his secret recipe, with herb and spices. The poison is gonna kill anyone that drinks even the smallest amount of wine from this bottle. This is a very powerful poison. It takes like a few hours to kill the person. The king had like 1,000 servants and 20 prisoners. And even though he's willing to kill his servant, he'd like to avoid it as much as possible, but he's willing to kill the prisoner. Those are like, this is a king, this is middle age, like the prisoner are like expendable. So he's willing to kill the prisoner, and he wants to find which is the bottle that is poisoned. So what should he do? Do someone have any idea? There is 1,000 bottles. Excuse me? Not too much, right? This needs to continue. Obviously, like the easy solution is like you get like the 20 prisoner and 980 servants to drink one bottle each, right? But this is gonna kill one of the servants, and we'd like to avoid that. So what we're gonna do is like we're gonna take 10 prisoners, and we're just like numbers all the bottle in binary. And if the bottle numbers as a 1, like we number each prisoner, and each prisoner corresponds to 1 digit. And if the digit is 1, the prisoner drinks, and if the digit is 0, the prisoner don't drink. And depending on the pattern of prisoners that are gonna die, you can find out what is the bottle that is poisoned. This is pretty optimal. Like there is even like 10 prisoners that's gonna make it. So that's pretty good. He's merciful. Anyway, the king is smart. He knows onboard information theory, so he can do that. And he throws a big party, and the big party is a huge success because nobody is poisoned except the prisoners. So the moral of the story is that if you code your information properly, you can put a lot of information in only a few bytes. And that's not always obvious to do it, but if you get a bit smart about it, you can do a lot. And it does matter because your cache is small, right? So you want to put as much information as you can in there. And that brings us to bitpacking. So the idea behind bitpacking is that you want to reduce the waste in memory. You want to reduce the amount of memory that you use, but you don't really use efficiently. And we're going to do that with a small cost in CPU. But as it turned out, the memory is vastly slower than the CPU. So if we don't go into some extreme, we're gonna make it good. This is where we make the difference between bitpacking and compression algorithm, right? Compression algorithms are trying to crunch as much data as possible as in a minimum space, though they don't really care about CPU cost. Here we want to make our program faster, so we want cheap CPU packing and unpacking of the data. So this is this kind of technique we're going to focus on. The first important stuff is going to be alignment. And alignment is very important. So maybe you're not familiar with it, but depending on the type of your data, they cannot be at any address in memory. And there is a very good reason for that, is that you don't want to load or store across a cache line boundary. Because as far as the hardware is concerned, those are two different data paths, and those need, in hardware, two different loads and two different stores. And depending on the hardware, it's going to be either super slow, because you do like twice as much memory access, or it's going to not work at all and give you some kind of failure. Usually it comes back to you as a form of a sick bus. So you should expect one of the two. The specific alignment is going to depend on the ABI, it's going to depend on the platform and the CPU we're working on, but a good rule of thumb is like for data that are a pointer and smaller, so I have like some rule of thumb here. Basically, the data that are the size of the pointer and smaller, the alignment is going to be the size of the data. Because if you align with the size of the data, you're never going to load across a cache line boundary, and this is what you want. And for data that are bigger than that, there is actually no, like usually the biggest register you have on your machine, if we exclude like vectorization and stuff like that, but like the general purpose register you have on your machine are the size of the pointer. And so you need to have two loads or two store anyway for bigger data. So for bigger data, the element is going to be the same as a pointer size integral. This is a rule of thumb. This is going to not be true. Like you can always find some weird platform where this is not the case. But on most platforms, this is what you are going to get.
Let's say that this size of is a power of 2. So
yes.
Like a 5 bytes, this size of, you shouldn't do it.
Yes. Well, there is very little platform where you have integral type that are not power of 2.
Integral type.
Yeah. So for struct, basically for struct, it boils down to what element do you have in your struct. And the element that have the largest alignment is going to fix the alignment of the struct, right? Because you want this specific element to be aligned. And then there is padding that is added between elements in the struct to make sure that each element have the correct alignment. And I have a small example on the next slide. So here I have a struct, and I have a uint in the struct that is taking 4 bytes, and I have 2 bools. And we see here that this struct has a pretty bad layout. It's wasting a lot of memory. Because we have a uint in there, so the alignment is going to be 4. And the alignment is the struct is going to be the alignment of the largest, like the element that have the largest element. And this is the element number 2. This is the uint. So the struct is going to be aligned 4. And first, you have a bool. It's going to take 1 byte. And then you have the uint, and the uint need to be aligned 4 as well. So you had 3 bytes of padding, and you had your uint. And then the next bool, 1 byte again, and you have a new padding. So here you basically waste 30%, like a third of the memory that this struct use, which is pretty bad, right? Because this memory, this memory is going to use cache, right? And you could put useful information in this cache instead of just padding to respect alignment. So maybe we can do something simple to this struct to greatly improve its memory efficiency. Do anyone have some idea? This is like, yeah.
Put the uint first.
Yes, exactly. So it says put the uint first, and this is exactly what I was going to propose. So you put the uint first, and the struct is 4 byte aligned, and the beginning of the struct is so 4 byte aligned as well. So you can have your uint, and then you have the bools. And some padding, but now there is only 2 bytes of waste. And so just by reordering the field of my struct, I have improved the information density I have in my memory by quite a lot. And now I can fit much more of those struct in my cache, or maybe something else. So there is much more information that can access fast, and it's going to make my program faster just by being a bit smart about how I order the field in the struct. So I have some tips. About how you do that well. You're going to start with the field with the largest alignment, typically. So this is what we did with the struct before. So those are the fields that have the biggest constraint. And if you order your fields from the one that have the largest alignment to the one that have the smallest alignment, you usually get a pretty good layout. There is other thing that you want to take into account. Usually you want to put the odd field first, so you may want to tweak that a bit, but generally that's a good first approximation of what you want to do. You want to make sure where you know where the pads are, because maybe if later you have some information to add, like if you know that there is a pad in this struct and you need to fit some information somewhere in your program, you may be tempted to add like some new data structure or what. But you're like, oh wait, I have some byte here in that structure that I'm not using. Maybe I can recycle some of this memory to put something useful there instead of creating some new place in memory where I put those. A good idea is to enforce, when you make assumptions about alignment and size of different things, you can enforce those using static assert. And there is two property you want to use for that. They exist on any variable. Those are align off and size off. They exist on variables and on types. And you can use those, like if you make an assumption, you order your field given some assumption about alignments of those various fields. You can make sure that those assumption remains true. And if something breaks those assumptions, you're going to know it at compile time because of the static assert, and you can see what you do about it. Classes actually are just like struct as far as alignment problem are concerned. You just have to consider them like struct, but at the beginning there is 2 pointers. One is the vtable for virtual function, and the other one is a monitor that we don't use that much. I think there is an ongoing effort to have it go away, but so far it's still there. As far, yeah. So because you already have those pointers at the beginning of the class is going to be already aligned at 8 byte or 4 byte, depending on if you are a 32 or 64-bit machine. So, but basically, if you consider it like, okay, I have a struct, and there is this field that I don't see that is magical at the beginning, and you're gonna do the right thing if you see it that way. So there is a term I've been using. Yes?
Can the compiler freely relocate members or not in an extern D class or struct? Is the compiler allowed to swap the order of members or not?
So as per the spec, the compiler is not allowed to change the layout of structs. However, it is allowed to change the layout of classes, but it doesn't do it right now.
Okay.
But the specs say that the compiler can.
Okay, thanks.
Yeah, so I've been using the term information density before, and I'm gonna try to talk a bit more about this. The information density is like how many actual bits of information I have compared to how many bits of information I'm using. So for instance, if I'm using a bool, I have just 1 bit of information. This is true or this is false. This is just 1 bit of information. But I'm using 8 bits of storage. So bool is like pretty poor information density. Often when you see a bool, you should be, maybe I can stick that somewhere. I can use some trick to stick that somewhere. An object, an object is going to be a reference, so it's a pointer. Typically, so this number is specific to x86 64 bits. Most of the number I have in there are x86 64 bits. The number may be different on other platforms, but it's the general idea, right? You can adapt the number, but roughly like the conclusion is going to be about the same. You have only 45 bits of information. On modern x86, you actually only have 48 bits of memory address. Like Intel is lying to you. Those are not 64-bit machines. Those are 48 bits. And the higher bits in the address are going to be either all 1 if you are in kernel space or all 0 if you are in user space. And so you have like 48 bits of actual address. And then you have the alignment, because this is an object, so you have a pointer, at least, for the virtual table in there. So you are 8-byte aligned. So you have like 3 bits, 3 least significant bits that are going to be 0. So at the end, you have only 45 bits of information, and using 64. So once again, maybe you can do something there. Like if you need to cram some more information, you can use that. If you want to have a good idea of the actual memory density that your application have, you can dump the memory of your application and zip the dump. And you compare the actual size of the dump with the zipped side. And the zip side is obviously like, it's kind of like the pie in the sky goal. You're like almost the ultimate information density. If you had like infinite computation power to decode your stuff, this is what you would be doing. And you try always to tend toward this number, even though you're never gonna reach it. I'm sorry.
Yeah. What happens if you dereference a pointer and you've messed up? What happens if you dereference a pointer when you've say all those zeros and ones for kernel and user space? Is that
bad things are going to happen if you do that. So you need to make sure of what you do, and you need to unmask those bits and restore the value before you dereference that pointer.
Yep.
You cannot use it as this. It's going to fault. Like if you change the most significant byte, it's going to fault. If you change the least significant byte, you're going to shift a bit in memory, and you're going to load what is like a few bytes after what you're actually intend to load. And it's going to be misaligned. So on some platform, it's going to fault, and some other, it's going to be slow. So to improve your information density, we're going to use bitpacking. So you tried some CPU consumption to do the packing and the unpacking against better memory usage. And usually, that's a good trade. When it comes to performance, always benchmark, but usually, most of the time, this is gonna be a win. So the bitpacking basically is you use one integral as a storage. So one integral is like one kind of integer type, right? So a uint, a ulong, or something like that. You use that as a storage. But instead of representing just a uint or a ulong, you are gonna specify what each bits belong to. And you use bitwise operation like shifting and masking to retrieve the information in this pack of bits that you're interested in. There is several facility in the standard library that you can use to help you with that. And the part of the standard library you're going to look at if you want to do this kind of stuff is std.bigint. So the basic of std.bigint is the Bitfield mixin. So this is a mixin you're going to put into struct or classes, and that allows you to create a mixin. So basically, here, I'm still using the example of the class we had before, which has an integral and 2 bools. But I'm going to just steal 2 bits from the uint. So it's only a 30-bit int instead of 32. And I'm using those 2 extra bits to put the 2 Boolean in there. And depending on your application, you want to do that or not, right? Because now you can only store number up to about 1 billion, and before you could go up to 4 billion. Statistically, most of the time, numbers are small. And so in many cases, it's actually acceptable to do this kind of stuff, especially if you have a significant win here. You basically divide by 2 the size of the struct. So obviously, the size of the uint now is not as big, and the access of the uint or the bool are not atomic anymore, right? Because you need to read them and then shift mask to find out the value. But shift mask are very fast operation on modern computer, and memory access are very slow operation on modern computer. So generally, you want to do this kind of stuff. Let's look a bit at what is generated. For an integer, you're going to get this code generation, basically, in D. So you're going to shift the integer to the right until the rightmost part of the integer match aligned with the 0. And then you are going to mask all the higher bits part of it when you read it. And then you get the value of this integer. And when you write it, same thing, you do some bitwise operation to clear the bits where this integral is in the bit field, and then insert the new value. For Booleans, there is a few tricks you can use to make that better, because it's just one bit you are interested in. So to read it, you can just mask and see if the result is equal to 0. If you think about it carefully, actually, if the check to know if it's equal or different from 0, most often it comes for free. On most architecture, you have a flag register. And when you do any kind of operation, those flags are going to be updated. And those flags are like, did an integer overflow happen? Is the result is 0? Is the result is positive or negative? This is like the kind of information you're going to find in those flag register. Most architecture have them. And so when you do the masking, most architecture are going to update the flag to say if the result of the masking is 0 or not. And so as the result, you have just basically one instruction. For writing, this is a way you can do it. It's going to be also simpler, right? Like the writing of an integral value was quite a complicated operation, actually. So this way, you can do it in a simpler manner. It's going to generate more efficient code. An alternative I've seen used is to use XOR operation to flip the bit. So you check if the bit is the value you expect, and if it's not the value you expect, you flip it using XOR. Both are like roughly equivalent in terms of code gen. So some tricks about how you lay out your bit field. There is two special spots in your bit field. There is the elements that are in the least significant bit. It's already at the right position in the bit field, so it doesn't need any shift. It needs only masking. So for this element, you're going to have faster read and write on this element. And the leftmost, you don't need to mask, because once you shifted it to the right, you've basically erased all other information in the bit field. So the leftmost doesn't need masking. So for the leftmost and the rightmost, you basically skip half of the operations. So those are nice spots you want to exploit. So you want to put the information that are the most useful and the most often accessed in those two extreme areas of the bit field. If you have large elements, you want to avoid having large masks in your code gen. Like, basically, large masks are going to be large integer with a lot of ones. And often in the code generation, you have different techniques to encode different size of integers. And the bigger integer means that the code gen is going to be bigger. So usually the biggest element, if it's a hot element, you want to put it on the most significant bit, so you shift it to the right and you get it. And you don't need large masks. Bool are always using masks. Though there is a trick, if a bool is in the most significant bit, and you consider the value as a sign, you can use a sign comparison to 0. And if it's 1, it's going to be negative, interpreted as negative. And if it's 0, it's going to be interpreted as positive. So there is a nice trick you can do if the 1 is the most significant bit. Sadly, the standard lib, the code that is generated by the bit field, don't take advantage of this. So that's kind of sad. But if you really care about some piece of code that is very important to you, you can use that. Generally, you don't want to put bools in special spot, though, because they're already faster than other fields to access. We have seen that you can use different techniques to access the bool, and they're already much faster than other fields, typically. So unless a bit is very, very hot in the bit field, in which case you put it in first position, otherwise you just like pack the bit field where there is nowhere else to put them. So a small example. You want to create a bit field and you want to put a flag in it, so a Boolean. You want to put an enum that have 4 value or less, so you need only 2 bits for this enum. And you would to put a 29-bit integer in this. So what is the kind of layout you want to use? Anyone? Yeah, let's assume that there is none of those elements that are especially hot. They are all used roughly equally.
I think it would be the enum in the least significant bits, then the flag, and then the integral in the most significant bits.
Yes. So unless you have some very specific constraint, like some field is especially hot or what, this is the kind of layout you want to have, and this is the code gen you're going to have for each field to be read. So this is going to be the most efficient combination for those. Like you see, like one of them only did masking with a very small constant, so that's good. The other one only needs shifting, and the flag can be checked only with a mask.
Same question. Is the Bitfield implementation allowed to, swap fields around?
Yes. So when you create the bit field here, the order you declare the stuff are going to be from the least significant bit to the most significant bit.
But is the bitmap allowed to change that? Do better than what I did? If I put the order wrong.
If you put them in that order, this is what it's going to generate, right? But if you change the order...
No. What I mean is the implementation or is the library, can it rewrite it itself?
No, the library is going to do what you tell it to do.
Okay.
It's not going to do anything else. Because as we see, there is something you want to do if some of those bits are hotter than other. And so there is like, sometimes you want to put them in a specific order.
To answer a little more, this is actually a power of D. C and C++ bit fields give too much freedom to the implementation. They can do reorderings, they can put unseen pad bits in between, but in D you get exactly what you want. And I think this is one of the reasons why the language does not have bit fields, but it's a library solution.
Yep. Yeah, if you wanted to make a version of that ordered the field automatically based on some heuristic, you could do that. Like this is not what the standard library is doing, but there is no thing that prevents doing that. So if you have unused bit, in the bit field, what you're going to do is like you still need to declare them, but you just give an empty string as a name, and so it's not going to generate anything for those. But you need to declare them. The bit field is going to complain if the size is not a power of 2. And this is to make sure that you control the layout, right? Like even the unused bit, you want to tell the thing where they are. A nice thing you can do is if you plan to embed this struct in some other struct, right? Or if you are in a class hierarchy or something, you have some class that are going to inherit from you. You can make this accessible to those guys by just making a field, that they're going to use and add some bit in there if they want. Something that we cannot do with the standard library, and that would be very nice, is to create a bit field, but to be able to explicitly say where the storage is. So in a child class, maybe I want to use this derived bit field that is 29 bits and add extra flags or extra information in there. But you have to do like all the bit manipulation manually. No, you cannot use the standard library goodness. So that's kind of something that I find liking in the standard library when doing this kind of stuff. This is how it looks like in practice. This is some extract from SDC source code. So this is simplified. There is a lot of missing code. The actual code is much more complex than that, but we're going to fit it on the slide, right? So you have a symbol, and there is a ton of different flags and stuff that exist in the symbol, and you have a derived field that is the 18 bits remaining in that bit field. And the symbols, all the different kind of symbols that inherit from the class symbols, they can use those bits to do something. And one of them that do so is the field symbol. So a field is like a field in a struct, right? Or a class. And a field needs to know what index it is in the struct or what index it is in the class. And basically, this is what we're going to store in there. So by design, SDC is going to be limited to like 200,000 and so fields in your class. If you put more than that, it's not going to work. I hope you don't have code that have more than that. But you probably have other problem if you do. So now let's talk pointers. As we talked before, there is a lot of bits that are in use in pointers. Let's do pointer, but in a trusted manner, something that is not going to explode on your face in some very unexpected way. So based on the alignment of the memory the pointer is pointing to, you know that some of the least significant bits are going to be 0. And you can use those bits to store something in there. So basically, you have like log2 align off. So if you have 8-bit alignment, you have 0 bits. And if you have 16, you have 1 bit. And if you have 32, 2 bits. 64, 3 bits, and so on. So you have basically, if you have a class, you don't know what is the alignment on the class, but you know that this is at least 2 or 3, depending on if you are in the 64 or 32-bit platform. Because you know that there is at least a virtual table pointer in there. And once again, there is various things in bitmanip that can help you tweak those bits in a useful manner. This thing is pretty cool, actually, because it's going to check at compile time what is the alignment of the memory you are pointing to, and it's going to prevent you to create bit fields that are actually unsafe. So it's going to check at compile time that you can put bit in there, and you are not going to screw, you're not going to screw up. You're not going to erase bits that are actually meaningful in the pointer. As we mentioned, misaligned pointers are like not very safe to use to begin with. They are going to like not even work on many platforms, so we consider that the pointer is aligned there. And this is, on the left, this is what the code looks like, and on the right, there is a little schema that explain, a little schema that explain why it is safe. So on the left, you see I've extracted some code. This is an extract of code from a red-black tree that I've written. A red-black tree is a kind of binary tree that makes sure that it's roughly balanced, not exactly, but it makes sure that the shortest branch is, the longest branch is at least twice, at most twice the shortest branch. Sorry, kind of confused here. So the longest branch is at most twice as long as the shortest branch. And to do that, it needs to store 1 extra bit per node, which is called the color, and it's going to be red or black, and this is why it's called a red-black tree. And one thing you can do that is very nice is instead of storing this bit in the node, you can store it on the pointer. And a lot of part of the algorithm is like, if this node is red and if this node is black, then do that. But if there are some other color, do something else, right? And on most red-black tree implementation, you have to dereference the pointer, go to the node, check the color. And maybe you're going to do nothing, right, because it's the wrong color. And this is pretty bad. Like, you access plenty of nodes that you shouldn't need to access. So if you store the bit in the pointer, you can check this bit on the pointer, know if it's the right color, and only if it's the right color, you're going to reach the node and do what you need to do. This actually play nice because you know that the alignment of some memory storage is going to be at most the same size as this memory storage, because the goal is to avoid loading and storing across cache line. So it's going to be the size of the thing or something smaller, which means that if you store some bit in there, as far as the garbage collector is concerned, you have an interior pointer. So if you have a struct, it looks like you are pointing at some element within the struct, which is legal indeed. You can take an element in the struct. Or if it's an array, if you cast the stuff to void bracket, a slice of void, you can take the first element, the address of the first element of that, and you get the void pointer that is basically equivalent to the pointer with the flag to 1. So as far as the garbage collector is concerned, like, he is happy. It looks like an interior pointer. It's not going to collect your object or anything. It's going to play nice. So you can use that like fearlessly, basically. The library is going to do all the dangerous stuff for you, and you can enjoy the result. If you feel a bit more adventurous, there is various things you can do. The first thing you can do if you're on a 64-bit platform is ask the allocator specifically for address in the lower 32-bit, and then just discard all the most significant bit of your pointer. Obviously, you need to do that only for some specific object. You cannot do that for everything because you are going to run out of memory, right? So you want to do that only for some selected objects that are very important to you. Some allocator can actually provide that. So jemalloc is one of them. This is actually used in, I don't know if you know LLVM, but this is a virtual machine we use at Facebook. And on x86, you can put address of code directly in the instruction. You have instruction with immediate value for address. But if you want to put 64-bit address, then the code gen becomes much bigger. So all the pieces of code that are JITed are going to be in the lower 32-bit of memory, and so we can put like just 32-bit address for call and branch and things like that. So that's actually pretty nice, but very dangerous. So if you use that and you get burned, that's not my fault. You can stay in the 64-bit word by just overriding the 16 most significant bit. They are all 0 unless you are the kernel, and they are all 1. But I'm assuming that most of you are not the kernel, so for you they are 0. You can hijack them and put whatever you want in there, and when you want to actually use the pointer, you put them back to 0. That's very dangerous. If you forgot to put them back to 0, that's segfault or bus error. And it's going to confuse the GC, because the GC is not going to see it. It's not going to understand this pointer anymore. So make sure you have an actual pointer, or you pin this memory, or you allocate it with something else than the GC, because the GC is going to happily collect this thing, and it's going to be gone when you want to use it. So same thing. It's dangerous. So use it's not my fault.
What's the difference between this and the previous slide when you're using only 1 bit in the pointer?
Well, I'm taking advantage of the alignment of the memory you are pointing to.
Ah.
And this is not as dangerous, because as far as the GC or the runtime or anything is concerned, it looks like a pointer that is within this memory allocation. So even though it doesn't look like a pointer to the start, like let's say I have a struct, and this struct is 8-byte aligned because there is a pointer somewhere in there. So any pointer to this struct, the 3 last bits are going to be 0. So I can put something else in there. And as far as everything is concerned, when the pointer scans the memory, for instance, and see this bit field, it's going to see a pointer to some element within the struct. So it's going to conclude that the struct is alive and not collect it.
Yeah, I guess I missed the whole part, being into the struct. Okay. Weird. Thanks.
So yeah, so there is some bits that you can use safely, and there is some bits that are much more dangerous to use. Those I use them all over the place. This is nice, use that. The other one, be careful. So it's been pretty dense so far. I've given you a lot of information, so now it's time for like the best joke, and I'm surprised that nobody did it yet, but so I had to do it. Okay, we want to crunch our data even more. Make things, yes?
One question here. Will you commit your red-black tree implementation to Phobos? Because it should be more efficient than what Phobos currently has, right?
Yeah, one of the problems I have with that, actually I think this could be an interesting addition to Phobos. One of the problems I have is that in some recent version of DMD, the size of static arrays have been limited. And I've been using like gigantic static arrays in the tests of this red-black tree to make sure I could control the memory layout and actually check what happens when you try to reach or not reach node to compare when they are out of your cache. And I could do that by specifying the layout by using gigantic static array. I know the compiler don't accept arrays that are more like 16K or something. I'm not sure the exact size, but there is a size beyond which the compiler is going to reject those arrays. So all the unit tests are not passing with the recent version of DMD. And so that doesn't sound good to merge into Phobos. So I would have to rewrite all the unit tests if we wanted to merge that. But yeah, overall, that would be an interesting stuff to merge, actually. So back to the thing. We want to pack more. And so now we have crunched, like we have used all the bit we could, so we need to be even more creative now if we want to make things smaller. And one thing we can do is use a context. And so we have this object that is a context that are like kind of a kitchen sink object. You're going to allocate stuff in there, and it's going to give you handler that don't mean anything by themselves, but given the handler plus the context, you can retrieve the information. And a good use case for this is identifier in the compiler. So this is kind of the IDE that Walter presented this morning, but pushed a bit further. Basically, you are going to allocate strings and unique them in the context. And the context is going to give you an identifier back for this string. And this string is going to be 32 bits. So compared to a string in D, that's the significant reduction. And in the compiler, for most of the time in the compiler, you don't care what the string actually is. You want to know, is it the same string or is it not the same string? And you just compare the two identifiers, and you can know if it's the same string or not. And only when it comes to talking to the user, actually, you care what the string actually is. When you want to generate error messages, for instance, you want to say, oh, this symbol is wrong because na. But when you generate code or when you do semantic analysis and all of that, you don't care what the string is. You care is the same string or not the same string. So put them all in the context, and the context is giving you an int. It also makes the GC very happy, because you have a ton of objects that don't have pointer in them anymore, so that don't need to be scanned when doing garbage collection. So that'll make garbage collection faster just by cluttering your context. That's good. So extract from SDC again. I have a struct that is name. Within it, there is an ID. This ID is produced by the context. And I can get back the string by passing the context down. And it's going to fetch the actual string from the context. And the context also makes sure that all the strings are zero terminated. So if you want to pass them to some C function, they are unique anyway, so that's not too expensive to do. On the context side, this is what it looks like. Like all this code, I kind of like always I train the code and I keep the gist out of them, right? Like the actual code is more complicated than that, a bit smarter, but this is the general idea, right? So in the context, you have a string, you give it to the context, it's gonna look, do I have it already internally? Yes, I'm giving you the same ID. Otherwise, I'm gonna create a new ID, I'm gonna store it in myself, and I'm gonna return you this new ID. And it makes sure that the string is 0 terminated. So this is nice. That means that everything that has an identifier are reused a lot, typically in source code, right? Like, you don't create variables and functions and never call them, or never use them. Or maybe you do, but like your program must not be very interesting if you do that a lot. You can declare a bunch of functions and not use them, but you know, that's on you. Typically, in the typical program, you're gonna reuse those a lot. And so you're gonna reuse the same ID a lot. And instead of duplicating the string everywhere and having it to compare everywhere, you can just having an integer and compare the integer. You can even do some nice thing like pre-filling the context with information you know you're gonna need. So typically what I do is like I pre-fill the thing that are in object.d that I need, all the keywords and all the operators and the thing like, you know, scope exists, scope success, and all of that. Like, so exist, success, all this kind of word, they are in there, they are pre-filled. And so I don't even need to query the context for those if I want to compare somewhere in the analysis. I want to say, like, is it a scope exit? I don't need to check what is the ID for exit. I can use it directly. So the idea is, like, I have a bunch of stuff that are already pre-filled. I have a function there. I generate an enum with basically everything that I want pre-filled. This is like a very simple code. On the side note, the get operator map and get keyword map are also used to generate the lexer. There is a lot of code generation going on in there. But meaning, like, if I change one of those functions, I get the lexer and the prefill updated and all of that. That's pretty nice. So now I need to do the lookup, so I can use the names to create a lookup table, same way. And I can create a template that is called built-in name. And this template is going to give you statically the ID of something that is already pre-filled. And with that, I can, like, for everything that I know I'm going to use at some point, I don't need to query the context. I just need to get some name and compare if it's the same name as what I expect. So that's nice. That saves a lot. But we can do, like, even more stuff. One thing, this is using SDC, this is using Clang as well. This is not my ID, actually. This is the Clang people ID, and I just ripped it off, because this is what open source is for. And if there is good ID, you should reuse them. Like, I mean, if you pretend it's yours, you are kind of an asshole, but if you reuse them, this is good. So one thing you want to do in a compiler is track the location. Everything you have in your compiler, all the expression, the statement, the declaration, all of that, you want to know where they come from, because when you analyze them, if you have any errors, you want to say to the user, hey, this is this stuff in that file that is wrong. And if you want to generate debug information, you also want to specify in the debug information where this code comes from. And so this stuff are everywhere. So you want them to be small, right? Because they're going to be in pretty much everything. Like every object that your compiler manipulates, there is some location in it. So the idea is pretty much the same, right? In the context, when you open a new file or start to process a new mixin or what, you give it to the context, and you're like, here is a new file I'm working on. Here is the content of the file. Here is how big it is. And the compiler is going to give you, here is the position where your file begins. And this is going to be an integer. And then you have, like, all the integer from whatever the context gives you up to this number plus the size of the file. And that would mean, like, every position, every byte in the file, basically. And so now you have a way to specify any position in the file. And with two of those, you can specify any range in the file. In addition, you use a flag. Well, this is actually how boss clang has decided to do it. There is an extra flag to say, hey, is this an actual source code? Is it an actual file where there is source code in, or is it some mixin or macro expansion? Like mixin for D and macro expansion for C++. And the both are registered separately. So the flag is checked, and then you go to look in the file, or you go to look in the macro to see where this position comes from. So as I mentioned, there is like 2 use cases for that, emitting debug information and error messages. And because of that, for error messages, we don't really care about performances that much. You're going to generate the error message and kit anyway. So you don't need to be especially fast. For debug information, this is a bit different, but we can make it fast anyway because you have a very predictable access pattern. Basically, you are going to do everything in one file, and you are going to generate the file line by line mostly. So to find what is the file and the line of some position, you have one element cache. So if I query the context and ask the context this position in what file it is, it have like a one element and what is the last file I queried, and just check. Is it the same? Yes. And 99% of the time, this is the same. So this is very quick. And then it does a bit of linear search, because often, like let's say for line, right? You are going to generate line by line, right? So often when this is not in the line, this is in the next one, or a few lines below, because the user made several empty lines or something. But so generally you're going to find it soon. So it's going to do a bit of linear search up to 8 elements, and then it's going to start a binary search, because then that means that we switch to something else. Maybe we got into a mixin, or maybe we start to process another file. And I made a small, schema to show what it looks like. So basically, number from 0 to 2 billions, the context is going to allocate some range of numbers for every single file you give to it. And this is a weird program, right? Because there is a lot of mixing in there. So I assume the green guy is using like std.regex or something. Yeah, typically you're going to use more file than mixing, but every time you give the context new stuff, and it's going to allocate a range of number. There is some limitation, but honestly, if you reach them, good for you. You cannot compile more than 2 GB of source code in a single unit, because it's not going to fit in the address space, plus 2 GB of macro or mixin expansion. This is a lot. This is a lot. And you probably, like, if you have this kind of amount of source code in D, I'm not sure they even exist, but if someone has this amount of source code in D, I discourage compile it all at once, unless you have terabytes of RAM. Yeah. So with a pair of location, you can specify any range in the file, so that's easy to track. The lexer, this is very easy to the lexer, right? Because as it gets new character, it can just bump the position by how many characters it lexed and gets the new position. And this is used by Clang and SDC, as I mentioned. So everybody's okay? I killed everybody, right? Like, too much information. I have some more, actually. So let's talk a bit about polymorphism. I don't know if you know those guys. Yeah, Barba Papa. They can change shape and everything. So one very easy thing you can do is a tag reference. So you have a pointer, but it can point to different things. Just put a tag in the alignment bits. If it cannot point to more than 8 different things, say, you're good. You can use reflection to do very nice stuff. One good use case of that is LLVM have call and invoke instruction. And an invoke instruction is basically a call that can throw. So there is some extra information in there. But most information, like, most are the same, right? Like, you have a function that you're calling, and you have some argument and stuff. And so you want to have some code that can take both a call or an invoke and do something with that, like query the argument and query the function that is called. And so they create this abstraction called call site, which is basically a pointer to either a call or an invoke, and a flag that says if it's a call or an invoke. And then you can forward to the function either of call or invoke. That's a very useful abstraction. One of the good things you get out of that is that you don't even need to do the virtual dispatch or what. You don't even need to dereference anything. You have it in the pointer, right? So you can get the type without dereferencing anything. If you had to do it in the, so I have to slide with some code. If you had to do it in D, this is pretty much what it looks like. So here you have the code to generate an enum with a tag for each different types. So this is going to generate an enum called tag, and you're going to have an entry for each different type you pass as a u ... here. And then you can use this enum to create a tagged reference. So you have a void star, that is the pointer, and you have a tag that indicates whatever type this pointer actually is. And I made a get function where I use a trick with a union and a sequence in there, but basically it's gonna just like cast in whatever type is appropriate and assert that this is the right type. And you can opt dispatch using a for each on all the value of the tags and all of the types. And just like if the different type have a method with the same name, then you can call that directly on the tag reference. And it's gonna call the right function. If you wanted to do that, like the actual code is checking that obviously you can call on both and everything, right? But it doesn't fit on the slide if I keep all the checks, so I remove them and I give you the gist of the ID. Let's get, yes, no, yes.
Sorry, just a quick question. The tag tuple on the fifth line, left-hand side.
Yeah, which
Sorry,
one?
what is tag tuple, like void star pointer tag tuple? Where does that come from? Did I miss something?
Oh, the tag tuple is come from there. This is like on the right, the last thing. And this is the entry in the Bitfield. You need to create that. Let's get into some crazy thing. Let's do some value type polymorphism. So if all the polymorphic elements you want to use, you can fit them all in like roughly the same budget in terms of memory. Then you can make that a value type with a tag to distinguish which one it is. And then some raw bytes that are going to be interpreted differently depending on which one it is. This is actually a basis for a lot of network protocol, but you can do that in memory, and it works very well. So you use the tag to different them. Yeah, so you can. This is what D is for, right? Like you can create those kind of atrocity where you have like plenty of raw bytes that don't mean anything or that mean like different things depending on the tag. You're gonna reinterpret them. You're like, this is completely type unsafe. You're gonna do all kind of crazy stuff there. But you put a nice interface on top of it, and it appears like a polymorphic type, and everything works great. And all the code that actually use that don't even need to know the kind of atrocity that is going on. And you can get something that is very, very compact in terms of memory. So to do that, the first thing you're going to do, there is two important code snippets in there. There is the size of Bitfield, which is something we probably should have in the std bitmanip, but right now we don't. So it takes the same kind of argument of a bitmanip, of the bitmanip bitfield, and is giving you the size of the bitfield in bits. And then there is another function that computes the size in bit you need to store all the value of an enum. This is super dumb code. There is nothing complicated about it. It goes over all the value of the enum. And look at the one that needs the more bits to be stored and return that. this is why it gets nice. So I'm using the stuff that are before to create a type descriptor. So this is going to be used in SDC to describe all the type system of D. And so there is many different types that have many different data in there to make them meaningful. But you know, like all those different data are going to be in the raw byte that don't mean anything. So those are the bytes that are called data there. And you have a kind and a qualifier. Like all D types have a type qualifier, and all D types have a kind that tells you what kind of type it is. Like, is it a struct? Is it a class? Is it a built-in type? Is it, you know, an alias? Whatever. It's going to give you what kind of type. And then you have data that are just raw bytes and are going to be interpreted differently. So to make type in SDC, you have this type descriptor, and you have an indirection field. The indirection field is a pointer. This is a raw pointer. And depending on the tag as well, it's going to mean different thing. Yeah, either like if you need too much data, let's say, you allocate and you put in the indirection field. But it's incredible how many types actually don't need any extra data. This is what it looks like roughly in memory. So you have like two pointer sized objects, say, in the struct. One is like some raw data, a qualifier, and a kind, which is the kind of the type. And then you have an indirection, which is a pointer to whatever. So this fits into 128-bit budget. This is a nice value type. You can stick it everywhere in every expression you want. Some type need extra space. This is why there is the indirection field. Most do not. And this replaced, so before that system, there was a class hierarchy, right? So you had the pointer type, and the pointer type was pointing to class type, and the class type were pointing to the class, right? And then you want to create that const, and you got to turtle all the way down and reconstruct all the way up, right? So there is a lot of pointer chasing going on. There is a lot of allocation going on. This is inefficient. Changing to that system makes things significantly faster, like about 20% faster. So that was a huge win. So you can do this kind of stuff. That pays off. But why stop here? When you do identifier resolution in a compiler, you get a type, an expression, or a symbol. So we can add one level to our hierarchy and create the identifiable type, which is anything that can be resolved when you resolve an identifier. So it's going to be a type, an expression, or a symbol. And if you add a tag to say which one it is, and you recycle the indirection field to store an expression or a symbol, then you're good. And you obtain that. And this is really good. Like, this saved a lot of template bloat, because before that, there was no type to return. You don't know what to return. And you cannot return like a pointer or something like that, because type were no value type, and the other one were reference type. So I had to pass a delegate down by alias and call it down the road, like all the way down in the identifier resolution, call that code back and do whatever is needed. So this was a lot of template bloat. So, you know, push it one level further. And this is what it looked like in practice, right? So you have the identifiable that come from the identifier resolution mechanism, and you can apply whatever you want with it. So this one is expecting an expression. So it does check. If it's an expression, yes, return it. If it's not an expression, then make an error. And so at the end, you have like kind of a class hierarchy that look like this. It's not a class hierarchy, obviously. It's all value types. But you represent like this hierarchy of different things with it. And that's very compact. It's very efficient. That's very good. ABI-wise, you want your struct to be 1 or 2 pointer-sized element. That's the best. Everything bigger than that is going to be passed in memory. And everything with more field than that all over the place is going to be passed in memory as well. So you want stuff to be passed in register to be fast. A common anti-pattern I see all over the place, including in my code, is like having 2 pointer size plus a bool. And this is bad. This is what changed from passing everything in register to passing everything to memory for 1 bit. That is sad. That is sad. Don't do that. We do even that in the standard library with std.bigint. We have an array in there and a bit sign. Like we have a Boolean for the sign of the stuff. And so everything is passed in memory instead of register. So sad face. Yep, pretty much it. 1 or 2 pointer sized, do that, it's gonna be fast. Good. I don't know, do we stop there? I have like a little bit extra, not that much, so I can blast through it or we can stop there. Yes, no?
Yeah, you can go for another 5 or 10.
Okay.
Especially if it's more content like this.
So we're going to do polymorphism with Struct and with tagging, so we can win a lot of place on all those monitors and vtable pointer. So you create a base struct, all the substruct, which would be like the subclass, the child class, I mean. I'm going to call them substruct. The first field of those substructs are going to be this base class, and you can alias this to the base class. So it implicitly casts to the base class. In the root class, you have a tag that is describing what type it is. And the tag can be part of a Bitfield if there is not too many different types. So like you can combine with everything that we talked about before, right? So the tag can be part of a Bitfield, and the subclass can reuse this Bitfield, or the root can be using this Bitfield. And then you use like various mixins template to make that work. Each leaf in the hierarchy is going to be one specific value in the tag. Each non-leaf is going to be like a range of value in the tag. And the root is going to be like all the possible value of the tag are going to match the root. To make that work, you need to know the hierarchy at compile time. So it's not always usable. Like if you want to provide a library to be extended by a user to provide new implementation of a class, this is not going to work. But if you know all the subclass you're going to have, this is something you can use. And yeah, you can use a bunch of mixins templates that are going to add static assert all over the place and everything that ensure that you do everything correctly. But in practice, this is what it looks like, and so this is not that bad. You can create like different classes and subclasses. In terms of memory layout, it's going to look like this. So you see that the memory layout of some child is compatible with the memory layout of the parent, right? So you can implicitly class the pointer up the chain. So it's safe to upcast. There is an alias this that allows you to upcast implicitly. If you want to dubcast to a leaf, that's very easy. You just check the cast is the right value, the tag is the right value. If it's the right value, then you know you have the leaf you are interested in. And if you want to subcast to some substruct that is not a leaf, you check that it's in the right range. If it's the range you win, you can subtype. This is much more efficient than downcasting with classes, because with classes, when you downcast, you need to go to the virtual table, get the type ID, and then follow the chain of type ID to find out if you can safely cast or not. So this is like you are chasing a linked list, and this is amongst the worst thing you can do to your CPU. So don't do that to your CPU. Comparing integer, the CPU like that, much more better than linked list. You can do virtual-ish dispatch, which is kind of virtual dispatch, right? But it's not really virtual dispatch. So there is no virtual table. There is a table with an entry for. There is a table per method, and in this table there is an entry per type. And then you use the tag as an index within this table. And this is used in HHVM for PHP arrays. So PHP arrays have a very creative data structure. Creative. Creative is a good word. In the sense that it's all data structure in one. It's a vector, it's a hash map, it's a set, it's a tuple, it's like whatever you want, and it's reverse. And if you do the very generic data structure, like in the original implementation of PHP, this is a hash table with a doubly linked list between all the elements of the hash table. And this is like the most inefficient data structure you can imagine. So it's much better if you can specialize depending on the use, right? And so you can use these techniques and with a tag to support the different use case of the array. And this is what HHVM is doing. So they have two small schema to compare like the virtual dispatch. So the regular virtual dispatch, you have a vtable. And in the vtable, you have one vtable per different types. And in the vtable, you have one entry per method for this type. And if you want to create a new type, you have a new vtable with all the same function in there. And when you want to call the function, you dereference the vtable pointer, you index to whatever method you want to call, and you dereference the method address, and then you call it. In our case, we do like virtualish dispatch, and we use the tag as index in an array, and there is an array per method. And so this is structured differently, but that works the same way, basically. You can like transparently call method, and depending on the type, it's going to call a different method. This is good because usually you have better locality, right? It's much more common to call the same method on a bunch of objects that may be of different types. Let's say you have a collection of objects and you want to print them all. So you're going to go over the collection and call the print method on each object, right? And it's going to call a different method for each object types. So it's going to hit a different virtual table every single time. So each of those virtual tables, either they take a lot of cache or they even maybe not be in cache. So that's a typical use case that's not very efficient. On the other end, you're going to have the table with all the print function that is very hot, and you're going to call like index in that method using the virtualish dispatch. So obviously, depending on the use case, that may be worse, right? You can have the opposite effect, but this is much more common than the opposite effect. So in most typical use cases, this works better. And if you cannot do that and you still stick with class, you can sort your class by type, and you're going to get roughly the same goodness effect. And the table for each method, they can be generated using the reflection in D. So you don't need to do much, right? Like the compiler is doing it all for you, granted library support, just like it would do it for actual classes. So this is relatively transparent to use. And there is a nice bonus for Walter and Daniel that want to use visitor. So if you go that road, you cannot extend new types. You need to know all the type at compile time. But you don't need to know all the method because there is one table per method. And so this is like the opposite situation you have with regular classes. With regular classes, you cannot add new function because it would change the table, the virtual table layout. But you can add new type as you want dynamically. This is the other way around. You cannot add new type dynamically. You can add new method dynamically. So you can generate new visitor all you want, and it's going to create like a table for all the visit function in the visitor, and you can virtualize dispatch in there. So that allows very efficient use for visitor. And now I'm done.
So I had one question some time ago. Couldn't we implement the bigint with using the bool in the text pointer?
Excuse me?
You've presented a text pointer, and to implement bigint, we have a pointer, we have a bool field. So we could improve it by using a text pointer.
Yes. So what I'm saying, we would have to benchmark it to know which solution is better, but you can stick the bit either by limiting the size of the slice, putting in the length field, and you could only have 2 billion elements in the slice, but I'm not even sure this is possible at all to begin with. So we are probably safe there. Or in the pointer, in one of the lower bit of the pointer, this is possible as well. I have no idea which one is faster. We should benchmark, but I think we should definitively do one of those.
When you were talking about contexts, I don't know if you'd seen, there's an interesting thing that Valve do with loading resources where they use relative pointers. And it's a similar sort of idea. So for that, they can have, say, a very complicated tree structure on disk, just as a file. And when they want to load that tree structure and have all the pointers just work, they just map it in.
Yeah, because you have the index, and there is like relative index in the stuff. So with the initial index plus minus, whatever indeed there, you can find elements. Yeah, that's pretty much the same idea. Like basically, your whole memory chunk is your context in this case.
So, you know, in terms of amicable competitive spirit, I really wanted to find something in your talk to annoy you about. I really couldn't, except for one part, which is, as a compiler writer, you should really know to trust your optimizer. And the point you made about the sign comparison being an optimization for the dispatch on the most significant bit. If you have a decent people optimizer, which you do and which we do, you will get the right result.
I didn't check that it does that one.
Oh, it does generate a test rex.
It does some crazy stuff. Though that one, the alternative, there is a control flow with a branch and different masking, so that's a pretty tough one. I'm not sure it's doing it.
It does. Say your Bitfield is in rex, it does generate test rex, JS, whatever. So it's the.
My point, more than trusting or not the compiler, is that either you can do it or the compiler can do it. But if you have a bool that is very hot, put it in the first position, because you can just like compare to 0 and get the value of the bits. And regardless of what the compiler is able to generate, if you don't put this bit in the first position, it's not going to happen anyway. So you need to know it.
Yeah, again, what you showed there, this is all seems like a perfect candidate for Phobos inclusion. And one thing to Daniel, the thing is, SDC is built to run on the latest DMD front end, so we don't use LDC to compile SDC. And therefore, we cannot count on the optimization being there. And since the code is used in SDC, we have to do most things by hand. So that is just the explanation for that.
DMD is doing it?
You will have worse problems than no, I don't think so.
Yeah. True. He said that if you're using DMD, you have worse optimization problem than the comparison with zero trick. Which is true.
Okay, I have a question about tagged pointers. If we want to use the upper 16 bits of the 64-bit pointer, couldn't we provide a wrapper for that as well in std.bigint, or is it not good to do that for future architectures?
There was a proposal to do that. I'm not sure if it's a good idea, because the bits you can use are highly target dependent. So the 16-bit are usable on x86, but depending on the platform, it may be a different number of bits, or it may be none at all, right? So this is going to be highly platform dependent, and this is also highly dangerous, right? Because the garbage collector is not going to see those pointers, and so you may end up with like using memory that have been freed by the garbage collector or what. So I think this is the kind of stuff, if you want to do it, you can do it, but I'm not sure we should promote that too much. Like, this is a useful toolbox, but this is an advanced and dangerous tool, right? So, you know, depends where we want to go, but I'm not sure this is a good idea. Okay.